Okay, welcome to the second part of 7.1. Today we're going to be talking about some more about unit conversions, some more about radians. We're going to get a little bit more in depth into arc length. And I said I fixed my pen, but it just broke again. So it's not a problem. And then we're going to finish off today with doing some applications of arc length. We're almost done with 7.1. We're almost going to finish it up today. We're going to finish it actually tomorrow instead with some area problems and again some more applications. And then we're going to move on to kind of standard trig where we get into sines, cosines, and tangents and stuff like that. So let's get into it. Hold on. Hold on, we got a slight problem right here. Some of you may be very talented at reading upside down, but for the rest of you anyway, let's go ahead and that's not going to cut it. All right, we're good. Here we go. More 7.1 today. So at the end of last time we were talking about arc length, we were talking about radius, and so I mentioned I don't really like formulas, and it's true. But for some of you may like formulas, and if you're the formula like loving type, we'll get them here, right? So 360 degrees, remember, is 2 pi radians. And, October, you're blocking my light, so I'm going to need you to go somewhere else. So if you're using unit conversions, you can say, again, likewise, that 180 degrees is pi radians. And the other formula that we used is to find the arc length. You just multiply how many radians you have by your radius. Okay, it's essentially also unit conversions. All right, so you can use these if you want. I don't usually prefer the formulas, but if you do, here they are. So what I want to start by talking about, and this is where there's an advantage to the online class instead of the face-to-face class, is I actually want to show something real quick. There's actually, the book, by the way, is a very good resource. You can use it for more than just the homework. The book is pretty good. And they have this nice little graphic that's going to show a lot of angles that we want to use. Okay, so this thing, you will want to spend some time copying this down in your notes. I'm not going to do it right now because there's no reason for me to do it. You have the book, you can do it right here. Put this in your notes right here in this section because we're going to be requiring familiarity essentially with all of these angles. And really all you need to focus on is the first quadrant. Okay? And anything after the first quadrant, you can just kind of logic your way to the other ones. So be familiar with these: 30 degrees, pi over 6, 45, pi over 4, stuff like that. And these other ones, we'll come into them, but we're not going to actually copy them down on the video. Okay, so moving on. That sheet's done. Moving on, let's do some more problems. And I really want to hone in on unit conversions. I don't remember what example number I was on. So let's just, I know we haven't done example 17 yet. So let's just call this example 17. And let's just do some unit conversions just to really hone in being able to do them. And as a reminder, if you're watching this as a video, one of the best ways to do these examples with me is to pause the video when I start the example, do it on your own, and then watch me do it afterwards. If you're watching it live, follow along. All right. So if we're converting, let's start with an easy one. Let's convert 2 meters to kilometers. So essentially what you do with unit conversions is you start with what you have. And you look at fractions. And just like when we try to find common denominators for fractions and we multiply by 1, so we might multiply by 2 divided by 2. We might multiply by 3 over 3 or 4 over 4, something like that. Here we're going to multiply by 1 in a separate way because there are 1,000 meters in 1 kilometer. Okay? So this is 1. It have different units on the top and different units on the bottom, but we're not changing anything. And now what happens is that the units cancel out with meters. So we're going to get 2 divided by 1,000 kilometers. And again, you can write this as a decimal, which will be 0.000. Sorry, tenth, hundredth, thousand. Scratch that 0, literally. 0.002, or you could simplify it as a fraction as 1 over 500. Okay, and that's essentially what we're going to be doing with these unit conversions, is just using these fractions like this to simplify some stuff. And then especially what's going to come in handy more in the end of the section, so in tomorrow's video, is converting multiple things in a row. So if we wanted to convert 5 days to minutes, of course you could just Google, well, how many minutes are there in a day, and multiply it by 5. But let's really get some practice with this style of converting units. So again, we're going to start with 5 days divided by 1. You don't have to divide it by 1s, but since we're multiplying fractions, having it as a fraction can be helpful. Okay, and then we need to put that into minutes. And again, unless you just are really good with numbers or very good at Googling, which you will not be able to do during your quizzes and exams, you're going to need to make days go to hours first. So we know how many hours are in a day, hopefully. If not, I'll refrain from saying any rude comments, okay? We know how many hours are in a day, so let's just go ahead and do that. So 1 day is 24 hours. And again, the way that we always have this corresponding, right? We're not writing 1 day divided by 24 hours. We want the days to cancel. 1 days, all right? So the days are going to cancel, right? And now we're going to have 5 times 24. We're going to have 120 hours. But again, we need to get to minutes. So we have hours on the top. Well, in 1 hour, there is 60 minutes. All right, good stuff, good stuff. And again, the hours are going to cancel. So to find out how many minutes are in 5 days, you just multiply all this stuff together, and the units are good to go. And you get 120 times 60 is going to be what? 7,200 minutes? And there you go. All right. So be very, very comfortable with unit conversions. And you might say, well, Jason, that's kind of boring. Why are you only giving me 2 examples? You have the power. You have the power right now. You can convert anything to anything. Convert 25 years to seconds. You get a lot of fractions. You can, just go for it, okay? But this is all we're going to do outside of degrees and radians, at least for this class, all right? But feel free. I know if you're ever bored at home, you just, start doing some unit conversions just for fun. All right, let's do some degrees and radians though, because really the important thing I want is degrees and radians right now. We'll have to do more unit conversions for other stuff later, actually, but for now we're good. So 45 degrees, and let's convert that to radians. So again, what we're going to do is say, well, we got 45 degrees. Well, how many degrees are there to a radian? And if you actually found out how many degrees there were to a radian, you'd get actually something pretty ugly. So what instead we're going to do is, zoom. 360 degrees, 2 pi radians, 180 degrees, pi. 1 radian is about 23.4562. All right, good work. But I need an exact answer. Don't approximate on me. All right, so we got 45 degrees divided by 1, and 180 degrees is the same as pi radians. And again, radians are dimensionless. You don't need to write the radians. A lot of times we will not write units for the radians. So then, of course, you just do a little simplification, and you get that 45 degrees goes into 180 degrees 4 times, and we're left with just pi over 4 radians. And 45 degrees is pi over 4, as we have on this cool little chart that you copied into your notes right here, this little blue guy. 45 degrees, pi over 4. All of you are very lucky. My face-to-face class, I tried to go through this. It was ugly. All right, so let's do a couple more. Let's go backwards. 5 pi over 4 radians, 2 degrees. So really just doing the same thing. Very, very similar, except for this time we don't have to draw it over 1. You could if you wanted complex fractions, fractions inside of fractions, but you don't have to. We have radians on the top. So we need to, yes, it's going to be 225. Very good. So we have pi radians. It's the same as 180 degrees. And again, you just do the multiplication. The pi's are going to cancel. 4 and 180 goes into that 45 times. 45 times 5 is 225. The only units left is that degree up there. We get 225 degrees. Okay. So that's so much for that. And then last, what letter am I on? I'm on part E. Part E is in excited for trigonometry. All right. So what we're going to have right here is one example that trips people up quite frequently. Excuse me. It's that if you have 3 radians and you want to translate them to degrees, because a lot of times people think that radians need pi's, and they don't. Okay? Radians don't need to have pi's. Degrees sometimes might have pi. Okay? 3 radians just means an angle that corresponds to 3 radii of length along the arc. Okay? So again, in this case, it's maybe a good idea, and it's maybe a good idea a lot of times to write the radians, even though you don't need to write the radians. It might be a good idea. And then again, pi radians is 180 degrees. Now the pi's aren't canceling because the original radian measure didn't have any pi's. Okay, so you just multiply this out, and you're going to get, what is that, 540 degrees? 540 over pi degrees? So that's kind of ugly. You might want to approximate this. You've typed that into a calculator, you get about 171.89 degrees, units, important. Okay. So that's it for unit conversion. Unit conversion review. Hopefully you are pretty good with it now, but if not, you can always email me. We can get more practice done because unit conversions will be very useful, especially for most of this chapter in general. All right, so let's move on. Example number 18, apparently, because I skipped to 17 because I didn't know where I was. Here we go. Draw in standard position. And I don't want you to lose your minds. You might say, wait a minute, I have been keeping up with all of these trig lectures, and we did this yesterday. What's the deal? Well, keep your socks on. We're going to talk about what the deal is soon. Okay, so just wait and be patient. Part A, 135 degrees. Part B is going to be negative 225 degrees. Okay, so again, we remember standard position as you draw the coordinate plane. 135 means we go up 90 and then over 45 more. If you're not good with this, again, you can see 135, it's chilling right there. As I said, being familiar with this is important, but if you're not familiar with it at this time, remember you can just break it up into little pieces. 90 degrees and 45 more brings you to 135. So we got this good looking gentle angle. We say gentleman, we don't say gentlewoman. I don't know. Anyway, and we got an angle over here, negative 225. We go down for the negative, 90 degrees, 180 degrees, 270, oh, that's too far. 180 degrees and then 45 more. And so now these two angles have something in common. If you remember your terminology from the paper that I just threw on the ground shortly ago, if you remember back this was also yesterday, where the angle ends is called the terminal side. If they have the same terminal side, exactly what was said in chat, they are coterminal. Okay, so these are coterminal angles. Let's define that. Two angles are coterminal if they have the same terminal side. Good. And while we're at it, let's do another definition. Something else that's really, really important and is going to be extremely important starting in 7.2, which we're getting into probably on Tuesday, is the idea of this angle right here. If you look at the terminal side, what is the angle that it makes with the x-axis? And that's called the reference angle. So this definition is honestly pretty garbage. It's a very technical definition, and you can write it down, but really once we look at a couple reference angles, you'll know exactly what a reference angle is. But anyway, the definition is that a reference angle is the smallest acute angle formed by the terminal side and the x-axis. So again, all this just means is this angle. The angle that you would normally think with the x-axis. And the reason why we have the verbiage of the smallest acute angle is because technically, right, this angle is also an angle with the x-axis. But that's not what we're talking about for reference angles. So let's just look at a couple examples right here with our good trusty friend figure 15. I love figure 15. Me and him go way back, or her. I don't know what sex figure 15 is. So of course, anything in the first quadrant then is going to have a reference angle of just itself. 30 degrees has a reference angle of 30 degrees. Over here, 150 degrees has a reference angle of 30 degrees. 210 degrees, this angle, is 30 degrees. Wait a minute. Hold up, Jason. What a coincidence. All of these orange angles have reference angles of 30 degrees. Wow. Who would have thought? Whoever wrote this book, man, they just stumbled upon some. Of course, they did it on purpose, right? So everything that's blue has a reference angle of 45 degrees. All right, they're all 45 degrees away from the x-axis. The green ones are all, I don't know what color that is, cyan. They're all 60 degrees away from the x-axis. Okay? And that's what reference angles are. We're going to be using them a ton. You're not really going to be confused about reference angles. Even if you are right now, you won't be soon, because we're going to use them so much that you'll get used to them real quick. All right. So let's do, this would have been a good thing to state. We're going to add a little side note to coterminal angles. What is an easy way, once you have one angle, what is an easy way to find another angle that's coterminal with the first angle? What you're going to do is add or subtract 360 degrees or 2 pi radians. All right. So if, for example, so you can write that down, you can just add or subtract 360 degrees or 2 pi radians. All right. So that's an easy thing to do. And of course, if one angle is coterminal with another and the second is coterminal with a third, they're all coterminal together. There are infinitely many coterminal angles. It's like how friendship isn't. I don't know. That's a terrible analogy. That's depressing. Let's not talk about that. Let's move on to example 19. Not actually our 19th example, but who's counting? We are apparently not counting. We have example number 19. Which is going to be find a coterminal angle in the interval 0 degrees to 360 degrees, or 0 radians to 2 pi radians. All right. And so if I give you a problem in degrees, answer me in degrees. If I give a problem in radians, answer in radians. I'm not going to mark you wrong if you don't, but it's good practice to become comfortable with both types of units. All right. So part A, 800 degrees. So we need to get a coterminal angle that's in this this nice region, 0 to 360 degrees. And that's going to be very common. Later on when we're solving trigonometric equations, that'll be chapter 9, I think. That's a fun chapter, by the way. All you guys are in for a treat when we get to chapter 9. I hope you're enjoying this material now. But all we can do is we just subtract 360. But if you got a bit of a head for numbers, subtracting 360 is not going to be enough to get us into this. All right. We need to subtract 2 circles worth. Yeah, subtract 720, and just as chat said, if we subtract 720, we're going to get 80 degrees. 80 degrees is an angle that's coterminal, that is in that desired region. Good. Okay, we got some other stuff. Part B, 750 degrees. You might be saying, this is too easy. I already know how to do this. We're going to do the same thing. Subtract 720 again. Again, 720 is just doing 360 twice. And what we're going to get is 30 degrees. All right. These are angles that are coterminal, that are in our desired interval. But before you start getting too comfortable is no good. What we're going to do is look at some, let's look at some radians. 13 pi over 6. If you subtract 360 degrees, you're going to have to do some unit conversions. And again, it's important to have practice doing it in radians. So, so we're going to subtract again. Instead of 360 degrees, we're going to subtract its equivalent in radians, which is 2 pi radians. And you might say, well, that's not helpful. We got a fraction subtracted by something that's not a fraction, but do not fret. We can turn this into a fraction. We need a common denominator. All right, so this thing, think of it as 2 pi divided by 1. We don't want a 1 on the denominator. We want a 6 on the denominator. But Wyoming is the equality state. What you do to the bottom, you must also do to the top. Multiply the top by 6 as well. So we have 13 pi over 6. Minus, you multiply that out, you get 12 pi over 6. So we had 13. You had 13 of them. We lost 12 of them. Now we have 1 pi left over 6, which is also 30 degrees. If you're not in Wyoming, you should still care about equality. Yes. Excellent. Very good. So, hope you got that down because I'm throwing that paper away until I upload the image to Canvas. And we're really done most of the stuff that we're going to do today. Not too much left. Let's do it one more time, though. In part... Oh, gosh darn it. Well, that's on the ground. Let's be safe. Part K. Part K is good. Negative 3 pi over 4. Again, remember that sometimes you might have negative degrees and you want to find an angle that's coterminal, that's positive. So instead of subtracting 2 pi, we are, of course, going to add 2 pi. And we want a common denominator again, so we need to get a 4 on the bottom. If we multiply 4 on the bottom, we have to get a 4 on the top. And we can just do it this way, negative 3 pi over 4, plus now 8 pi over 4. Negative 3 of them, plus 8 of them is going to be 5 of them. 5 pi over 4, our good friend 135 degrees is coming right back. Sorry, 225 degrees. Be very careful. 5 pi over 4. So those are some coterminal angles. So we've basically got 2 problems left and we're going to be done for the day. And that's going to be getting back into arc length. That's supposed to be an L. You can use your imagination. This is a mathematics trigonometry lecture, but also an imagination lecture. So I'm helping you expand your mind in believing that that's an L. So here we go. So if you want to find arc length, there's 2 steps. Step 1, find the angle in radians. And step 2 is going to be, you can use the formula. I hate this formula, but people love formulas, so I'll write it down. You can have it if you want. All right. So for this next problem, I was going to actually cheat and not have to write it down, but I realized I just made it up, so I can't use the book. Next problem is example. I really need to keep track of what numbers I'm on. I think I'm example 20. Who knows? The numbers don't matter. I'm never going to refer to these. Anyway, the numbers don't matter. Yeah, I hear that in a math class. Great. So get your pens ready. This is going to be a fair amount of writing. So assume, and this is an incorrect assumption, but let's assume it anyway, that the Earth's orbit around the sun is circular. And this is an incorrect assumption because it's elliptical, but we're not dealing with ellipses right now, so we're just going to assume circular. And so if the Earth completes approximately 0.002738 of its orbit per day, and the Earth, that's an E, is approximately 91.409 million miles from the sun, all right, I promise the question is coming. The question is, how many miles does the Earth travel per day relative to the sun? All right, so we're going to do a little bit of trig. Solve this. All right. So in this class, anytime you're doing an application problem, you're going to do one of 2 things. And as soon as you do one of 2 things, all the application goes away. And it just becomes a normal problem that you're used to doing. And here's the one of 2 things. Here are both of the 2 things. I'll spoil it. I'll give you the cheat for the rest of the semester. You either draw a circle or you draw a triangle. That's it. Okay? I just solved every application problem for you in this class. Draw a circle or triangle and you're good to go. So let's draw a circle. Why? Because we have a circular orbit. So here we go. Let's assume that this is the orbit of the Earth around the sun. Sun's chilling right here. And the Earth is this little guy over here. And it's moving. We're going around this way. Doesn't matter which way we go. And let's say after a day we go this far. So when we're asked, how far did we travel in a day? All we're being asked is what is the arc length of this circle, and then we just got to plug in some numbers. And this is kind of a hard drawing to do because 0.002738 is a small number, so really the slice should be smaller than that. But on the other hand, it's already too small. I can't write anything in it, so you don't have to draw things to scale. It's fine as long as you understand it's not to scale. Then the other thing you have to do before you start labeling things is be very careful with units. For example, the Earth is 91.409 million miles away from the sun. So Earth is here, it's far away. Earth is still here, same far away. And if you want, you can write 91.409, but it is imperative to remember that this is in the millions of miles. Okay? So next up, we have to figure out what our angle is. What our theta is. Very baby theta right there. Sorry if you can't see it. Because we're not given it. And you might say, oh, this is theta right here. But no, it's not. Okay, so be very careful. So what we're given is how many revolutions are completed in a single day. All right, so this is revolutions. 0.002738. We're going to deal with RPM on tomorrow's video, but this is revolutions, and we need to convert that to radians. Unit conversions. Perfect. Great, great, great. All right, so I'm running out of room. 1 revolution is how many radians? Well, 1 revolution is going all the way around a circle. That's 360 degrees, which is 2 pi radians. So, again, unit conversions, the revolutions cancel, and we're left with radians on the top. And you multiply these things out. Word of warning, it's in 99% of situations, this warning is useless. But in the 1% of situations, the warning is important. It's good practice to not round until you are done with a problem. There are some very few exceptions to this, but usually you don't want to round as you're doing a problem. You get rounding error, and that compounds and compounds, and your answer gets less and less accurate. So let's actually keep this as exact as possible. Our angle theta, we multiply this out, 2 pi. Let's multiply the 2 in, and you're going to get 0.05476. And then let's keep the pi at the end. All right, just so it's still an exact answer. Again, we already approximated at the very beginning, right? The problem information is approximating, but we don't want to approximate any more than we have to. Keep things as accurate. So remember how we find arc length. You find the angle in radians, check. And then you just say, well, it's that many radians times what a radius is. You just multiply it out. So the actual length is, no, Kat, you're not going to be drinking my water today. The actual length is, the arc length, if you will, is going to be 0.005476 pi times 91.409. And you're going to have to be very careful with this, but I don't want to spoil it for you. Let's just keep doing it this way. And you multiply that out with a calculator, and you're going to get something, 0.005476 times pi times 91.409. You're going to get approximately 1.573. So you have to be very, very careful with units. I'm saying that all the time here. Because is our answer, first off, our answer is most certainly not 1.573. But is our answer 1.573 miles? Does the Earth only move 1.5 miles a day? I don't think so. Remember that the problem is given in million miles. So our answer is going to have the same units. 1.573 million miles is what the Earth travels approximately in a single day. So if you're ever feeling lazy and you go, oh man, I need to go for a walk, I need to go for a run, just think, in a single day, you're traveling 1.5 million miles. So maybe that's worth being able to eat a pizza for or something. I don't know. All right, let's do the last problem of the day, and then we'll finish off with some area applications and angular speed tomorrow. We are on example 21. This one's kind of like a baby version of the previous problem. Start with the hard stuff, then we got to cool down. We already ran the marathon, and now we're going to go walk to the spa or something. I don't know. All right. Good, good. Google says it's approximately 1.6 million. Pretty close. Pretty good approximation. So, yeah, a little vocab here too. Find the arc length along a circle of radius 10 centimeters, subtended, that's one of my favorite words, by an angle of 215 degrees. And again, maybe you're not a superstar when it comes to remembering angles, but hey, we're back here in the book. Become familiar with this, become familiar with these angles. Or again, you could also say that you're going 180 degrees and then 35 more. Okay? So, all that subtended means is that we have an arc, and the arc of that circle covers the same amount as that angle. Okay, so really what it means is start drawing a 215 degree angle, which again is going to be 180 degrees plus 35 more. But it looks something like that. That's the portion of the circle that we're looking at. And again, the radius is going to be 10 centimeters. And we're curious, what is this arc length? And you might say, this is easy. We did this yesterday, essentially. And yeah, we did. But we're phrasing it a little differently. And to be honest, yesterday I kind of jumped the gun a little bit. I started talking about radians and I started getting excited about, hey, this is what a radian means. So here's where it's supposed to be. So again, the arc length is just how many radians and how much is a radius. Well, we got 215 degrees, and this is where you're going to go, whoa, oh my goodness. We have got this garbage unit called degrees. We need radians. Why are we dealing with this crap? So let's convert 215 degrees to radians. Again, unit conversions. 180 degrees is the same as pi radians. The degrees cancel out. And hold on. What is this? 43 pi over 36. I think it simplifies to. Again, you don't want to approximate until the end. Keep things exact as long as possible. And no, I'm not really going to mark you off. Unless you approximate so many times that your answer is just completely, whoa, sorry, light. Unless you approximate so badly that your answer is completely garbage. But it's good practice to be in. So that's our angle. That's our theta. So if we have that many radians and a radius is 10 centimeters, then our arc length is just going to be 10 centimeters times 43 pi over 36. And let's not write an equal sign. Now that this is our final step, let's find an approximate for that. 43 pi divided by 36 times 10, that is approximately 37.52. And again, units are important. The length is in centimeters. All right. And that is basically it. So you now have most of the material. You can start on 7.1. You should be pretty good to do almost the entire assignment. We're going to finish tomorrow. Tomorrow will be an even shorter video than today. Today was actually longer than I had planned. And then tomorrow will be a short video, and then we'll have another short one on Tuesday probably. All right, so good luck. And again, if you have any questions, please send me an email, or you can use the chat function on Canvas. And have a good day.